Now, sometimes when different numbers are related, we can say how they're related with ratios. Sometimes we can say how they're related with fractions. I won't do that one today, but we can also say how they're related with equations. So, for example, if I had the two numbers 20 and 40, I could say they're in the relationship 1 to 2, because one number is twice the other, or one number is half the other. But can you see how I could have written that with fractions? I could say that 20 is half of 40, or I could say that 40 is 2 times 20. So I can definitely give like a fractional type relationship there. But I'm going to show you how to turn relationships between numbers into equations. These ones that I have here, the numbers x, y, a, c, p, and q, I don't know what any of those numbers are, but not many of them are in a simple relationship. I suppose a and c are. A and c are in a fairly straightforward one. I know that whatever number a is 4 times bigger than whatever c is, but for the others, it's a slightly less obvious relationship. It's not quite as simple as whole number multiples. So all you have to do is you get the same number of parts. So I know that the number x represents 3 parts, the number y represents 5 parts, and then you think of the 3 times table and the 5 times table, and you try to find a common multiple for them. Ideally the lowest common multiple, but it need not be. And I know that the number 15 is in both times tables. I will find the number 15. So at the moment, this x is 3 parts. If I want to make it 15 parts, I'd need to multiply it by 5. Okay, so when it was just 1x, that was 3 parts, but if I multiply it by 5, I get 15 parts. In the same kind of way, this side of the ratio over here is a bit bigger already. It represents 5 parts. To get that up to 15 parts, I don't need to multiply it by quite so much, because it's already bigger. I only need to times it by 3 to get 5 parts up to 15 parts. Okay, so on the left, I've multiplied by 5. Okay, the x has got multiplied by 5 to get 15 parts, and on the right, the y has been multiplied by 3 to make it 15 parts. Now, you're used to doing the same to both sides of a ratio, and if you do the same to both sides of the ratio, it's still in the same ratio. I've done different things, so these two numbers, whatever they are now, are no longer in the ratio 3 to 5, because they're both 15 parts, but they are therefore equal. If they're both 15 parts, they are equal. And let's just recap what we've actually done there. I didn't know what the two numbers x and y actually were. Maybe x is the number 33, maybe y is the number 55, I'm not sure, but when you cancel the ratio down, you get 3 to 5. Maybe this was 300 and this was 500. I mean, I don't know, I've got no way of knowing, but when you simplify the ratio x to y, you end up with 3 to 5. What I did is turn the 3 parts into 15 parts, the 5 parts into 15 parts, and so because they're the same number of parts, we can say that they are equal. So what I've done is I've taken this ratio statement about how the numbers x and y are related. Still don't know what the numbers x and y actually are, but I've shown you how they're related with the ratio, and we've turned that into an equation instead. It's definitely not the only equation you could have chosen. You might just look at these two numbers up here and you say, well, okay, then I know that on the left here, that must be 3/5 of what I have on the right. So you could have said that x is 3/5 of y. And that's true, isn't it? Because earlier on I gave examples like maybe this is 33 and maybe this is 55. If it is, it's definitely true that 33 is 3/5 of 55. I said it could be 300 and 500. But yet 300 is indeed 3/5 of 500. So it absolutely could be. You could think that this relationship has come from this one, if you like, where you've just divided both sides by 5. Okay, if you take this equation here, divide both sides by 5, 5x becomes 1x, 3y becomes 3/5 of a y. You can write that as 3y over 5 if you like. No reason why not. That's the same thing. Lots of ways of writing this. And I could have divided both sides by 3, and then I'd have 5/3 of an x is y. So y is 5/3 of an x, if you like. There are even other ways. I decided to make these both 15 parts to begin with. I could have made them both 1 part. It's quite easy to make them both 1 part. If the left-hand side is currently representing 3 parts, I could divide it by 3, and then it'd be 1 part. So the left-hand side divided by 3. If I divide the right-hand side by 5, y over 5, then they'll be equal as well, won't they? Because they're both one part. So lots of ways you could think about that. In the same kind of way, if I want to turn this one into an equation sort of statement, I know that the left-hand side is 4 parts. I can make the right-hand side 4 parts as well. So the left is already 4 parts. If I times this by 4, 4c is 4 parts. Well, if they're both 4 parts, they're definitely equal. So a is equal to 4c. You could have also said 1/4 of a is 1c if you wanted to. Now finally, I just want to point out that it is acceptable to use the shortcut that you can times that by that, and it will be equal to that times that. You can absolutely do that, and that's a useful shortcut to use over here because I'm not actually sure what 13 times 9 is. I don't know my 13 times table at all. I do know my 9 times table, so I'm not sure what number is in the 13 times table and the 9 times table. Not sure of my common multiple, so but it doesn't really matter. I could just say, well, okay, if I times the p by 9 and I times the q by 13, then they're both the same number of parts. I'm not sure how many parts, but it's the same number, so they must be equal. And I've made an equation. I've turned this ratio into this equation. They are the same thing. Still don't know what the numbers p and q actually are, but I've turned an explanation about how they're related using ratios into an explanation about how they're related using an equation instead. Now, it's always tricky to know quite how much detail to include in one of these videos. If I say too much, that could be confusing. If I don't say enough, that could be confusing as well. I could have explained that whole thing in probably one quarter of the time, just giving you an example, but maybe you wouldn't have seen like quite why we do it the way we do. Hopefully, by giving you as much detail as I just did, you've got an idea of why the method actually works. We get the same number of parts on both sides. Therefore, we can say they're equal because they're the same number of parts. This was one of the examples I put on Google Classroom. It was a bit more flowery than this in the original situation, but the idea is I had some brown sweets and some white sweets in the packet. I tipped out the packet and found that they were in the ratio 3:1, but then I learned that Wilma had already eaten 2 of the whites, and before she'd eaten them, the original pack was in the ratio 5:2, brown to white. The way I might approach this is I say, well, I don't know how many browns there were originally, and I don't know how many whites there were originally. So let's say that B represents how many browns there were originally, and W represents how many whites there were originally. I've got absolutely no idea what these two numbers are, but I do know that they were in the relationship 5:2. So maybe there were 15 browns and 6 whites. That would work, wouldn't it, if you have both sides times by 3? But I've no idea what B and W are. Maybe it's 50 and 20. Okay, I really don't know. Let's turn that into an equation, though. I could say that 2B is the same as 5W, basically making them both 10 parts. I get 10 parts if I times this by 5, and I get 10 parts if I times this by 2. So there's an equation right there. Now I know that Wilma comes along and eats 2 of the whites, so there's still all of the original browns. There's still B browns in the bag. Still don't know what that is, but it hasn't changed. She hasn't eaten any of the browns. She ate 2 of the whites. Now there were originally W whites in the bag. If you eat 2 of them, there's now only W. Take 2 of them. Okay, and we know that's in the ratio 3:1. If I do my multiplying things, that times that equals that times that, or if you think about it by making 3 parts, well, this is already 3 parts, and times this one by 3, like so, they will be equal because they're both 3 parts. If I expand this out, I get that B is 3W take 6. Like so, and this is actually a pair of simultaneous equations. Now these two things that I've circled are simultaneous equations. You can write them in different ways. If I rearrange them, this one over here rearranges as 3W minus B equals 6. You can do that in more steps if you want to. You don't have to do that all in your head, but I've basically taken the B across and I've added the 6, and then I've written the left and the right the other way around. This one over here, I could take the 2b away from both sides, and then I'd be left with 0. So 5w take 2b would leave me with absolutely nothing. So I've just rearranged these two simultaneous equations to make them look a bit more like you're used to. I think what I'll do to solve this pair is I will double the top one. Okay, if I double the top one, that would give me 6w take 2b is 12, and then I'll use this pair to finally solve them. I will subtract these, and I will subtract upwards. So 6w take 5w is 1w. Minus 2b take away, minus 2b, nothing. And 12 take 0 is 12. Okay, so there were originally, w equals 12, that's telling me that originally there were 12 whites in the bag. I can put this anywhere I like. Maybe I'll substitute w equals 12 straight into here because it already says b equals, but you can put it into any of the equations you've found, it should still work. So I know that b equals 3 times w, so 3 times 12 takes 6. 3 12s are 36, take 6 is 30, so b equals 30. That's telling me that originally then there were 12 whites and 30 browns. Let's just see that that works, because if it does work, then we should have originally them in the ratio 5 to 2. So brown to white, I'm claiming that that's 30 and 12. Is that the ratio of 5? Yes, it is. If you divide both sides by 6, okay, divide both sides by 6, it does indeed give you 5 to 2. So that's correct. Does it still work if Wilma eats 2 of them? If she eats 2 whites, there's still all 30 of the browns, but we go from 12 whites down to 10 whites. That's 3 to 1, and yep, that works as well. So it does seem then that these numbers work for the whole thing, that if there were originally 12 whites and 30 browns, then that seems to be the correct setup for this. So I think that although there's lots of ways of solving a problem like this, these are classic GCSE style questions now where you have a ratio, the ratio somehow changes additively or subtractively. So, you know, we might add some more browns in, or we've taken some whites out in this case. So we've added and subtracted, and you know that ratios don't really respond to adding and subtracting in the way that you would expect, because they could completely change. 5 to 2 has become 3 to 1. We can't see what's been multiplied by. It's not obvious at all. I would suggest, although there's lots of ways you could do it, I think the algebraic approach is probably the best way of doing it. You can always turn ratios into equations, and you already know how to solve equations. It might sometimes be a bit of a sledgehammer to crack a walnut. What I mean by that is you might find a much easier way. I maybe could have solved this original question with something basic like lowest common multiple. I could have listed out multiples of the ratio, so I could have had 5 to 2, then 10 to 4, then 15 to 6, and just listing out my times tables basically and look for how they match up. Might have been easier, but the algebra will always work. We already know how to solve simultaneous equations. It's just a tool that you can use. It will always work, even if it's a little bit over the top for some of the questions. Right, good luck with these then.